I don't know what that means.
Like I went through and I finished the problem, there was check my work button, and I hit it and it told me if it was right or right before I went to the next question.
That was for the 3 tries for each question.
Yeah.
And then you had the 3 tries for the homework assignment.
Yeah.
Interesting. I have no idea. I would say that's a bonus for you. Don't tell me about it. Because that could potentially get you more points that way. But yeah, I don't know. I have no idea what that is.
I know for online homework, and
Yeah.
they would just tell you like, hey, this is what you did wrong, try to look at it.
Yeah, well, you should be getting feedback on what you got wrong, sort of.
Yeah.
I didn't know that I really, yeah.
It took me half
In any case, you get some feedback that way. Counted as a bonus. Hopefully that doesn't hurt your homework score. Because I think you only lose points for doing a full homework assignment a second time. I think is how it's set up. But I'm not even sure about that because it's really not clear. Okay. We already talked about the lecture text sequence. But I guess since that didn't get recorded, we can kind of mention that. What did I say section 3 was about? You all remember, right? You just talked about it. Don't you have it memorized already? Oh, someone did. Okay. We're looking at how it's connected to kinetics. Section 1 was, I actually don't remember, I think format. Something along those lines. Format or the basics of your equilibrium. 2 is a manipulation. So what kind of things can you do with the equilibrium constant? What rules apply to it? 4 was Q, or the reaction coefficient. 5 is Le Chatelier's principle. And I've actually slightly rearranged the slides to include the Chatlier a little bit before we talk about Q. And then 2 is again a manipulation, but it's kind of some of the more advanced manipulations that you will probably only see on this first exam. Okay? So they're relatively derivable from the earlier principles that we talked about yesterday. And they aren't that big of a deal because you won't see them all that often, okay, in the rest of the chapters. So we'll discuss them. I can say I taught you them, and then you can swiftly forget them. Okay. So one of the first things I wanted to go back to and review was kind of the quick interpretations from looking at an equilibrium constant. Okay. Remember, to get the equilibrium constant, it's the concentration of products over the concentration of reactants. Roughly. Okay. We say roughly because you also have the exponential values in there that changes that relationship, so it's not always a 1-for-1. Okay, so we can't always interpret based off of this, but if we're much greater than 1 or much less than 1, we can get a little bit more interpretation. Okay? So when you go through and run a problem and you find out that the concentration of your products is massive in comparison to the concentration of reactants, when you go through and punch that into the calculator, you should get a K value that is very, very big. Because if your product concentration is large over a small number, you get a big number. Yes?
When you say very big, like how big?
So it varies. Officially, it's supposed to be greater than 1. If it's a 1-to-1 relationship, so we don't have any exponents in it, it'll be greater than 1. As soon as you throw in exponential values, that messes with your calculation a little bit. You lose some of that interpretation ability. So when we're looking at big, order of 10 to the 4. Okay, so K would be larger than 1. We're looking at probably something on that order. Okay, that gives us that kind of interpretation. And that's saying a very large difference between those. Okay, it's hard to come up with an exact number on this because a lot of it just comes from experience in working with the questions. And I haven't worked enough problems to specifically say, oh, this is exactly where it works. And it makes it even more difficult because if we change the reaction and put in exponential values, we also lose some of that interpretation ability. In general, if your products are greater than your reactants, as far as your concentrations, your K value should be greater than 1. Some level greater than 1. Okay? And that may seem like such a minor thing, like, oh, well, that'll never be important. everything is based around 1. So as big as we can get greater than 1, how small can we get less than 1? And remember, k, the smallest k could be would be 0. How many numbers can be greater than 1? An infinite amount. How many numbers could be between k equals 0 and 1? Still infinite. Okay, so we have an infinite number of possibilities either direction. So that 1 value does give us some information, allows us to quickly give a rough approximation to this. Okay? If we went through and looked at our reactant concentrations and we saw that our reactant concentration was much bigger than our product concentration, when we go back to our equilibrium expression, we would have a small number divided by a big number, which gives us a really small number. And that's where we would get k being less than 1. Okay? Again, with the order on that, and this 10 to the minus 4 will come into play a little bit later when we get into some estimation stuff, which I think we'll look at on Thursday. K should officially be greater than or equal to 0. That gives us, again, an ability to quickly interpret see what we get, so that when we punch in the calculator and we get a number, we can quickly look at it and say, yes, this number makes sense, or this number makes absolutely no sense. At that point, you've got a couple options. When it comes to the homework, what should you do? If you punch it in, you get a number that doesn't make sense to you. Okay, what I would do is take all the work that you did, set it aside, flip it over so you can't look at it, and do it again, beginning to end. No notes. Okay? The reason being that if you made a mistake in your original work, it's not going to be easy to see it, particularly because how much paper do you take up when you write out a problem? Probably take up a couple lines, maybe something about that size. Okay? Trying to see your work and see where a simple mistake was made, not easy. Okay? If you're instead doing your work on a whiteboard where it's massive and you can see everything, then fine, check your work. Otherwise, put your work aside, try the problem again. If you get the exact same answer, now you're kind of stuck. Okay? At that point, I would say you can either push to the textbook, try and look through your notes to see what went wrong, send me an email. Say, hey, I'm really having trouble with this. Okay? On an exam, slightly different circumstance. What should you do if you get a number that doesn't make sense? Go to the next problem. You already messed it up once. Continuing to work on it likely just means that you're going to mess it up again. Okay? Then you're going to continue to work on it and get frustrated and irritated and spend 20 minutes on one problem when you could have spent that 20 minutes solving 15 other problems. Okay? The only time that you should go back and redo a problem is when you have time at the end of the exam, once you've gone through everything. Okay? Can't emphasize that enough when it comes to exam test taking. Okay? So use these approximations to kind of help you double check your work. It should get you pretty close, or at least eliminate a few answers. The next thing that we looked at was actually Q. I want to step away from Q for the moment because in the process of talking about Q, I realized that we didn't address another more important issue. Okay? The Chatlier came along. I'm pretty sure you guys haven't seen the Chatlier's principle yet, right? Okay. For some reason, I thought it was covered in 151, but that doesn't make sense. Okay? The Chatlier's principle. So what he ended up observing is that if you took an individual reaction and it wasn't at equilibrium, the reaction would naturally, on its own, react until it reached equilibrium, every single time. Every single reaction is going to drive towards that equilibrium point. We don't know when that point is reached, but every reaction is going to push towards that point. Okay? He added to this a little bit further and said that if once you're at equilibrium and you mess with the reaction and shift it off of equilibrium, it says, well, fine, I'm going to go back to equilibrium. And it's going to do whatever it needs to do to be able to shift back to equilibrium. Okay? And we'll look at all the different variables that can change this and force this to occur in different rates, or different fashions. We've got some of them listed up here. You've got your concentration, pressure, and temperature. We would expect all of those to affect your equilibrium. Why? What happens if you change the concentration? If we just plugged it randomly into our expression, the K value changes. Okay? What happens if we change the pressure? Same deal. If we just randomly plugged it into the equation, assuming we weren't or were at equilibrium, our K value would again change. Okay? So concentration and pressure all directly impact your equilibrium constant. When we look at temperature, what happens when you change the temperature? Okay? We said heat could be a term either released or absorbed by the reaction, so it's effectively either a product or a reactant, respectively, which means it's also going to affect our equilibrium constant. Okay? So these three things, we'll look at various derivations on how they come into play and what effects they end up doing. Okay? Kind of summarized a little bit neater, in my opinion, would be if you're not at equilibrium, then it's going to get to equilibrium. Okay? The reaction will do whatever it needs to do to reach equilibrium. Okay? So with this principle, we can now evaluate the idea of Q. Okay? And that's our unequilibrium unconstant. And that's because when we're looking at Q, we're not at equilibrium concentrations, so it's unequilibrium. And because we're not at equilibrium, we know the reaction is going to start to change our reaction concentrations in products. We're also not constant. Okay? So what's the use of this? Well, Q, also known as the reaction quotient, is solved for effectively the same way. Concentration of products over reactants. Okay? And with Le Chatelier's principle, we know that we want Q to be K. The reaction is going to do whatever it needs to do to become the equilibrium constant. So given some initial conditions, we can try and decide, is it at equilibrium or not? Okay? So if we went through and plugged it in and we put in our products over reactants, we would get a number. Okay? If we had then a K to compare to, so let's say we have K. Okay, same idea, products over reactants. Let's say that Q was a bigger number than K. Whoops. So mathematically what we're saying, Q bigger than K. How does that value get bigger than the equilibrium constant? What has to happen? The concentration of products has to be greater when we calculate Q than when we calculate K. Okay, remember, our reaction wants to travel towards our equilibrium constant. So to do that, what has to happen? To get Q equal to K, what do we have to do? Okay, we would need to drop the concentration of the products. Where do those products end up going? Remember, our reaction's in a closed system. We can't just remove things from it. The reaction's going to do everything on its own. We tweak it off of equilibrium, and it does what it needs to. So what happens to make the product concentration smaller? Makes the reactant concentration bigger. So as we drop the products, our Q gets smaller. Our reactant concentration also goes up, which means Q gets smaller still, 1 divided by a larger number. So a small change between our product and reactant concentration results in a large difference in our Q or K value. So what's the end result? If Q is bigger than K, we said our product concentration was too big. One of the other things we could have said was our reactant concentration was too small. Why did you pick products out of curiosity and not reactants? The product concentration is easier to relate. It is a direct relationship. If we increase products, Q has to increase. If we decrease products, Q has to decrease. It's a lot easier of a relationship. So we go back to our equation or our relationship. If Q is bigger than K, that means our product concentration is too large. What do we have to do? Decrease the product concentration. The way the reaction will do that, I guess I should write out a reaction here. So if we got our reactants in equilibrium with our products, Okay, and actually officially I guess we aren't at equilibrium yet. Okay, if we look at, we'll just put an arrow in there, or just a line. If we're now going to test, are we at equilibrium or not, we can just plug in our numbers for our concentration values and see what we get. Okay, we can then compare that to K. If the value is too big, what does that mean the reaction must do? Product concentration must drop. How does it drop? Let's get really fancy with our words. What is that? Okay, that's closer to what I wanted. The reaction goes the other way. Goes the reverse direction. Okay, if we're going to get really fancy with it. So our reverse reaction is favored. Okay, so our reaction will shift to form more reactants or get rid of products. Does that make sense? What happens if Q equals K? It's at equilibrium, which means Q is K. There's no shift in the equilibrium. Everything is there. We're already there. The reaction quotient is our equilibrium value. No change. Okay, we're already happy. What happens if Q is bigger than K? Sorry, Q and K are too similar for me. If Q is smaller than K, so one of the things that we could do, and this is exactly how I end up remembering this. For some reason, I understand Q being bigger than K a lot easier than Q being smaller. If it's the opposite result of the one we already talked about, what does that mean? When we go back to our equation, we need to form more products. Our reaction runs in the forward direction. Does that make sense? Mathematically, if we go back to it, how does Q get to be a really small number? So we've got two ways to look at it. I think reactants are really big. It's an inverse relationship, not the easiest to deal with. So let's go back to products. Product concentration would be really, really low. So what has to happen to get to K? I have to increase the product concentration. To increase the product concentration, what happens with our reaction? Runs in the forward direction. Does that make sense? We're going to look at some numbers for these in just a second here. So I just want to make sure we get kind of a sort of okay understanding with what we've got here. Everyone's kind of happy with it? Ready to see all sorts of fun numbers get thrown at you? Yes?
Did we already talk about, or should we know how to get the concentration of product for reactant?
Not directly yet. So at this point, we're assuming it's going to be given to you. Yeah, I'm leaving that out intentionally at this point. The textbook also waits for a little bit on this too. So far as solving for product concentration or reactant concentration, that information would be given to you. You'd either be told it's at equilibrium, or you'd be told it's not at equilibrium. If it's not at equilibrium, what would you be solving for? Q. If it's at equilibrium, what do you have the ability to solve for? K. So at this point, that's all we're dealing with. We're just looking at those numbers, getting a kind of an understanding of what's happening with it. We'll look at the dynamics behind it in a little bit. Other questions on that? So some examples. We'll work the first one together, and then I'll let you guys work on the next two on your own. So at 100 degrees Celsius, the equilibrium constant for the reaction, remember how we talked about yesterday, said the equation would be provided to you, or it would be clear what the equation was. In this case, the equation's given to you, so you know what all your coefficients are. Tells us what the equilibrium constant. It has the value of K sub C equal 2.19 times 10 to the negative 10. What is the C stand for? Concentration. So when we plug in our values, we would expect to be plugging in concentration terms. Are the following mixtures at equilibrium when at 100 degrees Celsius? what direction will the reaction proceed if not at equilibrium? So one of the first things that I would flag, kind of what we talked about yesterday, is the temperature the same? Yeah, that means that we can solve this. If the temperatures were different, we're kind of SOL. Okay, we wouldn't have a way to relate those concentrations back to the equilibrium constant. Yes?
What's the concentration value of carbon dioxide in place C?
We'll get to that as soon as we solve the first one. But it is equal to the concentration of chlorine. For some reason, the spacing is a little bit odd. They're equal to each other. So, to solve, what would we need to do? Okay, we could look for to see if it's Q or K. So I wouldn't actually say find Q or find K. We actually already know what K is. So what we want to do is go through and come up with an expression that says we're either solving for Q or K. To solve for either of those, what is it equal to? Concentration of our products over the concentration of our reactants. What were our products? So we're looking at the concentration of carbon monoxide and the chlorine, right? And whoops. And chlorine. What are the exponential values for each of those terms? How do you know they're 1? No coefficients in our balanced equation. Technically, there's a 1 as a coefficient, but I guess kind of beside the point. Divided by the concentration of our reactants. What are our reactants? COCl2. What's the exponent on that one? Also 1 because coefficient again. We now have an expression. When we plug our numbers in, we can now punch them into the calculator and get a magic number out of this and decide what it is. Okay? I'm going to kind of guess you can do that. So if I did this right, let's make sure. So 3.3 times 10 to the minus 6 is our carbon monoxide. 6.62 times 10 to the minus 6 is our chlorine divided by 2 times 10 to the third. And we should get a number out of that. Assuming I can type into the calculator correctly, we get this number. Everybody agree to get that number? Throw it out there. One of the reasons why this problem can become difficult, or why 152 becomes difficult, is the order of operations when entering things into the calculator. So you need to make sure that you're very, very careful with when you're putting your multiplication and division in. Primarily, in this case, whenever you're dealing with division, the standard format would be 3.3 times 10 to the minus 6 times 6.62 times 10 to the minus 6. Everybody does that right. Then they hit divide by 2 times 10 to the minus 3. What's the problem with that? Okay. That 10 to the minus 3 is still in the denominator, which means you would have to include parentheses around that term. Okay, when you enter it into the calculator. Just pointing that out. Hopefully you're aware of that easy mistake. Another thing that I would do here to kind of approximate, make sure that we don't have a big calculator mistake, and this is typically what I do with all of these, is we can set this equation, pull this apart into 3.3 times 6.62 divided by 2 times 10 to the minus 6, 10 to the minus 6 over 10 to the minus 3. Why do I end up doing this? What's 10 to the minus 6 times 10 to the minus 6? That's 10 to the minus 6 plus minus 6, which gives us minus 12. So it's a mathematical equivalency divided by 10 to the minus 3. So again, we could plug it into the calculator, or can I get this term up into the numerator? How would I do that? 10 to the, what was it, minus 12 is the same as 10 to the minus, oops, now plus 3. We flip the sign on it. What happens? The same rule that gets us to minus 12, we can now add these two terms and we get 10 to the minus 9. Is that close to this value? Yes, that gets us pretty close. Will it be 100% accurate every single time? No, why not? You have to account for this term as well. When you go through and look at this term, you end up seeing an extra decimal point pop up, and that's where you get the 10 to the minus 8. Okay? It's an approximation that I use. If you don't want to use it, by all means, don't use it. Okay? I'm just trying to give you some other thing that you can use to approximate your answers and kind of help you out with that. Make sense? Okay, so we've got, let's go ahead and erase all of that now. We've got a value, 1.09 times 10 to the minus 8. 9, 8, 8. Okay? Is that Q or K? It's Q. How do you know it's Q? Because it's not equal to 2.19 times 10 to the minus 10. So what we could go through and do, let's see if I did this right, we would say that's Q. Next part of the question is which direction will the reaction proceed? Okay, so to figure this out, what we need to do is compare those two terms. Which one's bigger, which one's smaller? 10 to the minus 10, really big number, really small number? Really small number. 10 to the minus, keep saying 9. 8, is that smaller or bigger? It's bigger, so what we've got is that Q, come on, well, okay, that works. Q is bigger than K, which means the reverse reaction occurs, which means our reactants are favored in this course, or in the course of this. We get the backwards reaction. Our reaction goes, oh no, I did that right. Reaction goes left. 3 different ways we can say the exact same thing. Kind of get a feel for what you're doing with the numbers? Do it again. If you got questions, raise your hand. I'll give you 60 seconds to go through and work on this one on your own. Like I said, if you got questions, just raise your hand. I'll come around and help you out. Take a look at it and see what you're missing. And this is a good spot to go ahead and stop recording.